Hey everyone, and welcome to this online video. This is our first and maybe only online lecture for this semester, but it's supposed to make up for the missed lecture that we're going to have on Monday, October 28th. I'm going to be out of town, and I wanted to make sure that we covered all the material that we'd planned to cover. We were supposed to go over two sections that day. Section 3.11, which is the end of Chapter 3. It's on hyperbolic functions. And the beginning of Chapter 4, Section 4.1, we were planning on just covering the first half of that section. So I've broken this up into several mini lectures just so I could be able to upload all of this stuff to YouTube. So we're going to be starting with Section 3.11 here. And again, I'm going to apologize for my handwriting in advance here. This this device that I'm using doesn't lend itself to very easy handwriting here. So section 3.11 on hyperbolic functions. Just as a reminder, this section is not on Exam 2. Exam 2 only covers through section 3.9 on related rates. But you will need to know this material and the beginning of section 4.1 when we come back to class on Wednesday. Make sure that you know this, because when we start talking about stuff on Wednesday, I'm going to start into the middle of section 4.1, and you're going to need to make sure that you feel comfortable with this material. It's also going to be on the next WebAssign assignment, so make sure you take a look at this before Wednesday. This first video, I just want to give a little bit of motivation for what hyperbolic functions are, in the sense of why we look for them. If you remember back when we were developing our list of differentiation rules, we developed two lists. One of them was a list of kinds of functions that we could differentiate, like x to the n, or e to the x, or arctangent of x. And the other list was a list of combinations of functions, things like the product rule, or the quotient rule, or chain rule. I mentioned when we finished up logarithms that those lists were basically done, and that's true, but there are two functions that we haven't talked about that actually end up coming up a lot in the context of taking derivatives. They come up when eventually you end up studying a topic called differential equations. They'll end up coming up a lot. You'll probably see them at the end of Calculus 2. You probably will also likely see them at the a lot in a course called differential equations. So these functions that we haven't seen yet, that I want to introduce here, will come up a lot, and so it's important for us to take a look at them. So what I'm going to do in this first video is just motivate them a little bit by showing you why it is that we're looking for these functions in the first place. And to do that, we'll go back to a couple of familiar and comfortable functions, sine and cosine. And these have a nice relationship that the derivative of sine is cosine, and the derivative of cosine, this is almost a really nice relationship. We don't quite get the original function back. We end up having a negative sign there, and as you've experienced, that negative sign ends up being your nemesis. When you're differentiating, we constantly have to be watching out for the fact that this is a co-function, so we get a negative there. It would really be nice if we had two functions, f and g, where when I differentiated one, I got the other, and when I differentiated the second, I would go back and get the first. And if you think about some functions that you actually know some functions that do this. Now there's a silly function that does this. If you take the derivative of the 0 function, it's just 0, and then the derivative of the 0 function is 0, and that's not really useful. So if we think a little deeper, there's a nice function that we know that has this property. It's your favorite function when it comes to derivatives. It's the e to the x function. So if I differentiate e to the x, I get e to the x. And then if I come along over here and differentiate e to the x again, I get e to the x. Now this seems a little cheap too, because here the two functions that we're looking for are just the same function. E to the x doesn't change. If we modify this a little bit though, and look at the function e to the negative x, differentiating this we need the chain rule, so we do derivative of the outer, and then we plug in the inner, and then the derivative of the inner is -1, so I'm just going to stick a negative out front here. And if we differentiate that function that came out, you'll see that I have a negative derivative of the outer, plug in the inner, and then the derivative of the inner ends up giving me another negative, which turns that into a positive. So this is actually the same function as the one that I originally had. So both of these functions kind of act the way that we're interested in having them act. The one drawback that the one thing that they don't have is that these two functions, sine and cosine, actually have some nice symmetry. Sine is an odd function and cosine is an even function. If you remember the way that e to the x and e to the minus x look, they don't have any type of symmetry like that. So e to the x doesn't look the same if you flip it over the y-axis or if you rotate it around the origin. E to the minus x, same thing. So we don't have any symmetry going on here. So it would be nice if perhaps there was some way to combine these two functions to end up getting something that has some nice symmetry. And it turns out that's possible. And those two functions that we're going to create to have those properties are called hyperbolic sine and hyperbolic cosine. We're going to define hyperbolic sine, which we're going to symbolize as sine with an h there. This is also sometimes called sinh, just to make this short instead of saying hyperbolic sine. We're going to define that as e to the x minus e to the minus x over 2. You can also have that 1/2, just make it a 1/2 out front instead of dividing by 2. Oops. That's supposed to be minus instead of plus. Scratch that out there. So e to the x minus e to the minus x over 2. And the other function is called hyperbolic cosine. This is also called cosh. So cosh of x, or hyperbolic cosine, it looks very similar, except there's a plus sign there. So e to the x plus e to the minus x over 2. Or you can have the half out front, either one. These are the same way to express these functions. So these two functions turn out to have the nice properties that if I differentiate sinh, I get cosh, and if I differentiate cosh, I get sinh, and sinh of x turns out to be odd, and cosh of x turns out to be even. So these have the nice properties that we're looking for, and I'll show those to you in the next video.